Welcome back. So we talked about two benefits of overparameterization. First of all, it in some sense provides us with free variance reduction. Therefore, we can expect faster convergence for stochastic gradient descent and its extensions. We also talk about conditions under which overparameterization could help us to enjoy a condition we call the gradient domination or the PL condition. And as a consequence, not only we converge faster, but we converge to better solutions. Okay. As I mentioned previously, these are questions about training performance. Okay, so it doesn't tell us anything about how well we are doing on test or on thin data. Okay, and this is what we're going to talk about in this part of the lecture. So we're going to see that again under certain assumptions, certain conditions, overparameterization can also aid us with better generalization. The main idea is that overparameterized models enjoy what we call implicit regularization when they are solved with methods based on stochastic gradient descent. Okay. Now we talked about regularization previously in previous lectures, and we talked about this connection to generalization. So in particular, when we regularize a model, it improves the generalization performance, a widely known and accepted concept in machine learning and theoretical machine learning. Now we're going to show that if you have overparameterization plus gradient-based method, you get regularization implicitly. So therefore, implicitly, we are regularizing, and therefore we are improving the generalization of our model. Okay, so this again highlights the fact that the methods we are using to optimize deep learning models matter. Okay, so in fact, if you recall, in the very first lecture, we sort of included training by SGD-based method as part of the definition of deep learning. Okay, so because again these methods are crucial, not only in terms of bringing computational efficiency into the table, but also in terms of nice properties that they bring with itself when it comes to, again, finding global solutions to the training problem, as well as ensuring our models perform very well at test time. Okay? So for the rest of the lecture, we're going to explore this idea. And first, for simplicity, to make sure that we understand what is happening, we're going to limit ourselves to linear models, okay? And then I'm going to make a few comments about how people have sort of generalized this idea to arbitrary deep learning models, okay? So for the rest of this discussion then, we're going to stick to linear models. What does that mean? It means that the model that we talk about depends on, which is a parametric model, takes the input feature, and then sort of gives us a prediction, is linear. So it's just W transpose Xi. Okay, so it's the inner product between these two vectors. In particular, is some sort of projection, if you will. Okay. Now we're going to make an assumption that well, the number of parameters is larger than n. And note that in this case, because we have a linear model, D, the number of parameters, is exactly equal to P, which is the size of features. Okay. So what is our training task? We are again minimizing the average loss with the square loss because it's a regression problem. So this is the what we have to solve. Okay. Again, in matrix form, this is what's gonna be. Okay. Now in this case, it is a natural question to ask, what is the tangent kernel we talked about previously? So it turns out that the tangent kernel is going to be basically XX transpose. Okay, so it is constant along the trajectory. So that's an observation. It does not depend on W. So if I want this to have a nice condition to ensure the PL condition holds, I want the data to have a nice condition. It doesn't matter how I initialize my model, as long as the data is nice, then this matrix has a minimum eigenvalue which is strictly positive. It is fixed along the trajectory. So my method will enjoy fast convergence rates. Okay, so that's basically one consideration. Another consideration is that this is a linear model, so it is a convex optimization problem. Okay, so we can find one solution quite effectively, let's say, with any method, even black box method for convex optimization. But we're going to focus on gradient-based solutions to basically talk about the implicit regularization of these methods that appear when our models are overparameterized. Okay? And finally, again, it goes without saying that because we have overparameterization, despite the fact that it's a convex problem, there are many solutions. Okay? In particular, this is an underdetermined system of equations. All right. So the system is underdetermined due to overparameterization, which, as we talked about before, it means that we can perfectly fit all the data points, okay, such that in this case, when we have a perfect fit, the minimum function value is 0. Okay. All right. Now let's make an assumption that the tangent kernel is positive definite, meaning that the minimum eigenvalue is strictly positive. Again, this can be ensured if the data is nice, okay, and well conditioned. So if that's the case, then as we talked about in the previous part, the PL condition holds for any W. Furthermore, the loss is a quadratic loss, so it means that it is smooth. Okay. So the consequence, therefore, is that we have a convex problem. The loss is smooth. The PL condition also holds. So that means that gradient-based methods like SGD or gradient descent, in this case, can find an optimal solution. Okay. So in particular, just to simplify the discussion, we're going to stick to gradient descent, but similar ideas transcend beyond this case. So if I run gradient descent with this update, I go from the current solution to the next one by following the direction of the negative gradient times some learning rate, which is less than the reciprocal of the smoothness constant. If I keep doing this, at the limit, I'm going to find a solution for which the function value is 0. Okay. So that means that at the limit, gradient descent can find an optimal solution. Okay. So let's call the solution W hat. Okay. So we can get a function value which is 0, which means that we get a perfect fit to the training data. And in matrix notation, it basically means that y is equal to x W hat precisely. Okay. Now, what we're going to show is that among all possible solutions, let's call them W star, the solution that the gradient descent finds, W hat, is the one that is closest to initialization. Okay. So what does that mean? It means that the norm difference of W hat and W1, the point at which we initialize the algorithm, is less than the norm difference of W star and W1, where W star is basically an optimal solution here, which is not equal to the one found by gradient descent. Okay. All right. So therefore, what is happening here? So we actually, if equation 22 holds, something that we're going to show in the next slides, then implicitly gradient descent is solving a regularized problem. So in particular, the problem that it's trying to solve is that find a solution that fits the data perfectly, such that it has the minimum distance with the initial solution W1. Okay, or equivalently, we can, in terms of a constraint problem, we can talk about it as again like a regularized problem. Okay, so we can say that what we are trying to do is that we are minimizing the average loss plus L2 regularization. Okay, in particular, we force the model not to deviate too much from initialization. Okay. So there you go. This basically is saying that if we have an overparameterized model with gradient descent as our training mechanism, we have this regularization sort of phenomenon appearing implicitly. Therefore, we can attribute this to the fact that overparameterized deep brain models tend to generalize quite well to the test data as the overparameterization ratio increases. All right. So in the next couple of slides, then we're going to talk about equation 22. In particular, how can we show that among all solutions, gradient descent converges to the one that is closest to the initialization? Okay, and to do that, we need some linear algebra. So very, very simple concepts you've seen before, but I'm just going to mention it here, and we're going to mention that in the context of our training problem, minimizing the average loss for this specific overparameterized linear model. Okay. So I'm going to bring your attention to two concepts in particular, the range of a matrix and the null space of a matrix. Okay? So the range of a matrix is basically the set of all vectors that can be written as a linear combination of the columns of matrix X. Okay? So in particular, and this is what we're going to use, that if I have a vector A that can be written as the product of my matrix and some other vector, that vector will be in the range of X because it is indeed written as a linear combination of the columns of X. Okay, so that's one concept, the range. Null space of a matrix is basically the set of all vectors such that if I multiply them with X, the answer is 0. Okay. And for a matrix X, we have the fact that the range of X transpose and the null space of X are orthogonal. So what does that mean? It means that if I have a point B, okay, which belongs to the null space of X, its projection onto the range of the X transpose is 0. And furthermore, if A belongs to the range of X transpose, its projection onto the null space of X is 0. Okay, so these are basically what we need from linear algebra for the remainder of our discussion. Now for our problem, okay. So what are some vectors of interest? Okay, so for our problem, we first know that this is basically a condition that holds for an optimal solution, okay? Because we have an overparameterized problem, more unknowns than knowns, an underdetermined system. In particular, all of this means that this matrix X that we defined is a fat matrix. Okay? So it looks like something like this. It has more columns than rows. So X is something like this. Okay? And matrices like this, the fat matrices that have more columns than rows, have non-trivial null spaces. It means that there are vectors that are non-zero and belong to the null space of X. Okay. Right. So that's basically one fact about our problem. Another fact is that if I define a vector like this, W bar, which is X dagger times Y, well, this will be in the range of X transpose. Okay. So what is X dagger here? X dagger is basically the pseudo inverse of our matrix X. Okay. And again, the reason that this holds is that, well, go to the definition of X dagger. I have X transpose. So here, so it means that I can write W bar as X transpose times some vector A. Okay. Therefore, this means that W bar will be in the range of X transpose because it can be written as a linear combination of columns of X transpose. Okay, so that's another fact. Similarly, what is the gradient? So you can show simply that the gradient is going to be given by this expression. Again, some basic matrix calculus. Again, when we look at the structure of the gradient, we see that it is some vector times X transpose. So it means that the gradient is also in the range of X transpose. Okay, so that's basically another fact. All right, and finally, as we talked about, this is an underdetermined system, which means that there are many solutions. Okay, not just one, infinitely many solutions. It turns out that the set of all solutions can be written as W bar, what we defined earlier, which is essentially the intuitive thing you do. When I give you a linear system and I ask you to find the unknown, you take the inverse of the matrix and then multiply with the observation, right? So in this case, the matrix is fat, so you have to use the pseudo-inverse as opposed to the actual inverse, which does not exist, okay? Now, there are many solutions. They can all be written as the natural solution, W bar, plus any arbitrary vector from the null space of matrix X. Okay? So this is the set of all solutions. Okay? And notably, this intuitive, the natural solution, if you will, W bar, belongs to the range of X transpose. And as we just talked about, the range of X transpose is orthogonal to the null space, and also the null space of X is orthogonal to the range of X transpose. So therefore, the implication is that the projection of every single of these optimal solutions onto the range of X transpose will be precisely W bar, because B belongs to the null space of X, null space of X orthogonal to the range of X transpose. Therefore, when I take this projection, B completely goes out of the picture. Okay, so this is basically all we need to for the next slide, where we're going to show that equation 22 holds. In particular, among all solutions, the one that gradient descent finds is closest to the initialization. Okay, so let's recall that this is the object of gradient descent. Okay, so quite simple. And we just mentioned that the gradient belongs to the range of X transpose because it can be written as a linear combination of columns of X transpose. Okay, then if we put all of this together, basically we can see that quite simply the projection of the limiting solution W hat onto the null space of X is exactly equal to the projection of any iterate WT onto the null space of X. And that's also equal to the projection of the initialization onto the null space. Okay? So in particular, the projection of the solution onto null space is preserved as we are updating the solution. And the reason for that is that the update vector that we are using is the gradient, belongs to the range of X transpose, so it is orthogonal to the null space. So it doesn't affect the projection of the of our iterates onto the null space. In other words, the optimization is actually happening in the range of X transpose. Okay, so I'm just keep updating whatever my solution is in the range of X transpose. I'm not changing anything about the component of my solution in the null space of X. Okay. All right. Now we're going to leverage this as well as the facts we said in the previous slide to furnish the fact that, again, among all solutions, the one found by gradient is closest to the initialization. Okay, so in particular, again, let's start with this distance. Okay, so I'm interested in the distance from initialization for an arbitrary solution W star and basically the solution found by the gradient descent. Okay. And I'm gonna basically assume that W star can be written as W bar plus B for some vector B. Okay. And W bar was basically the natural solution, the inverse solution we get by a matrix inversion. And this is so kind of different than what the gradient descent finds. Okay. All right. So let's look at this this norm square. Okay. Well, the first thing we do is actually quite elementary. We can use the Pythagorean theorems. Okay. So Pythagorean theorem is basically saying that if I have like a triangle like this, okay. So if this is A, B, C, I have A squared equal B squared plus C squared. So this is what we are doing with just heavy notation. Okay. So range of X transpose and null space of X are orthogonal, which means that when I'm interested in the norm of W star minus W1, I can use the Pythagorean theorem to write this norm as the norm of the component belonging to the null space squared plus the norm of the component belonging to the range of X transpose squared. Okay, so that's what we are doing, Pythagorean theorem. Now, we're gonna get a very trivial lower bound by just dropping this term in orange. So both terms are positive, non-negative. So I can drop this one in particular and get a lower bound. Okay, so very trivial thing to do. Now, going from here to here, I claim that I can basically change this W star here to W hat. Okay. So in particular, the projection of W star onto the range of X transpose is exactly equal to the projection of W hat onto the range of X transpose. Okay. Why is that? Well, recall that we said all solutions can be written as the natural matrix inversion solution WR plus some vector chosen from the null space. Okay, so it means that therefore, when I do this projection onto the range of X transpose, the vector from the null space that distinguishes these solutions is gonna basically vanish completely, such that the component of all of these solutions that belongs to the range of X transpose is actually the same. So I can therefore replace this W star with W hat and get exact equality here. Okay, so that's what we use. The fact we use to make progress, and to go from here to here, I claim that I can add this term, this positive term, seemingly positive term, without making any change. Okay. The idea is that this term that I'm adding is actually 0. Okay. Why is it 0? It is 0 basically. I think this has to be equation 25. So it is 0 due to equation 25. As we mentioned, given that our update vector, the gradient, belongs to the range of X transpose, optimization and our modification of the initialization only happens in the range of X transpose. So therefore, the projection of all of the iterates, in particular the initialization as well as the limiting solution W hat, are all identical, such that this difference is equal to 0, and therefore its norm square is also 0. So I add that, nothing changes. Well, then we can again use the Pythagorean theorem. Okay, so I have basically B squared plus C squared, that's equal to A squared. Okay, so I have the component in the range of X transpose squared plus the norm of the component in the null space of X squared. These two subspaces are orthogonal. Therefore, this is going to be precisely the norm of W hat minus W1 squared. Okay, so therefore we established that critical inequality that said that among all solutions, the one found by gradient descent is closest to the initialization, which was basically key for our claim that when we have an overparameterized model and we train that with gradient-based methods, we are enjoying implicit regularization. Okay, so we basically demonstrated the implicit bias, implicit regularization of gradient-based methods for linear models. A natural question is that what happens when you have deeper models, right? So can we expect similar things to hold? And the answer is yes, under certain conditions. Okay. So here is the general template of how to go about this. So let's consider the general task. Again, for simplicity, you can assume it's a regression task. You have some model, and you want to fit the data. So this is our training task, minimizing the average loss, written compactly in this form as well. Now, to apply your previous results, one thing you can do is to naturally linearize the model, okay, around the initialization. Once you do that, you get a linear model. And we just showed that for linear models, nice things happen. In particular, gradient-based methods have implicit regularization. Okay. After doing that, again, our results hold for linear models. In particular, you're gonna deal with this linear regression task. Well, it is kind of almost identical to what we had before, except that now we have W minus W1, the initialization, and then we also need to account for this linearization by changing our vector of prediction to y tilde. Okay, so this kind of becomes the prediction error at initialization. Okay. All right. So for this linear model, what we just talked about is going to hold. So gradient descent will enjoy implicit regularization. Okay. Now, how can we claim that similar things happen for general models? Well, we have to crucially leverage overparameterization and the fact that we are using SGD-based methods with the small learning rates to show that if our model, let's say, is a shallow model or has some other favorable structures, the Taylor approximation error is basically very, very small. Okay. So the fact that we are linearizing our model using first order Taylor approximation does not change the model by a significant amount. Okay, and in particular, by imposing certain assumptions, you can show that we can control the approximation error by increasing the overparameterization ratio. In particular, we can show that the approximation error is small, and it kind of behaves with something like this. So this basically is saying that as the number of parameters increases compared to n, model becomes more and more overparameterized. Therefore, the approximation error becomes smaller. Okay. One way to achieve this is to consider, let's say, a shallow neural network, where you have a model with, let's say, one hidden layer or two hidden layers. Okay, and then you increase the widths of the model, meaning that you increase the number of neurons per layer. As the number of neurons per layer goes to infinity, the model becomes more and more overparameterized, and this approximation becomes smaller. Therefore, we can make a claim that our results for linear model in terms of their implicit regularization also applies to deeper models, thanks to, again, overparameterization. This brings us to the end of this lecture. So as a summary, we talk about the importance of overparameterization when it comes to training as well as generalization of deep learning models. In particular, we show that when we train these models with gradient-based methods such as SGD and its variants under the overparameterization regime, our methods enjoy faster convergence thanks to free variance reduction. They converge to better solutions thanks to the PL condition. And finally, they also generalize well thanks to implicit regularization. All right. So in the next lecture, we're going to talk about a different kind of training tasks that we haven't paid too much attention to, and that's basically the min-max optimization scenarios that crucially arise in the context of training generative adversarial networks. I'll see you in that lecture.